Good afternoon, everybody. Welcome to the latest CIBSE ANZ webinar, as we're now running the basically state-based ones, all nationally or even internationally, if you're that way inclined to dial in. Today's presentation will be on thermal energy metering technology. This is a CIBSE accredited presentation, which means Brent and his presentation have actually been independently reviewed by a CIBSE panel. So everything you do here today that is on screen has been approved as for Brent's words. As long as he chooses those wisely, I'm sure that's all absolute gold as well. I would, what's happened there? Apologies, we just had a presentation failure. Okay, I hope we're back in now. Everybody, we've just happened here. Ah, there we are. Okay. Brent, we've still got that back up, don't we?
Yes.
Lovely. Okay, there we go. Although we are doing this via webinar, I'd like to acknowledge the Gadigal of the Eora Nation, traditional custodians of the land that we're on today, and also acknowledge traditional owners of lands that you're all dialing in from via the conference, paying my respect to elders past, present, and emerging. Couple of quick admin slides before we go through to the formalities. CIBSE membership, research shows, and whenever research shows you need to listen. Professional registration, that gives you a huge advantage over unregistered peers. It can boost salary prospects, career progression, and give you better opportunities for professional development. Right now, CIBSE are hosting a professional membership and registration webinar on Tuesday, the 19th of May next week, and is free to join. The webinar is going to cover benefits of professional membership and registration, qualification requirements for iEng and CEng, how to go about writing your engineering practice report, which is the bulk of that application, about the interview process, and it'll also give you an opportunity to go through a live Q&A with the membership and development team, as well as the ANZ Business Development Manager, Sharon Pistongi, and technical support from industry expert, Steve Hennessy. You can register at cibse.org.au, and if the time doesn't suit, these seminars are actually available to deliver to your offices, or even your remote offices as well. So please do reach out to me or anyone else on the committee if you'd like to go ahead with that. Next up, we have the CIBSE ANZ Young Engineers Awards. So 2020 so far has clearly been a very challenging year between the bushfires early on and now the social distancing restrictions presented by COVID-19. At this stage, the awards are still running, and they're a very important way to not only raise the profile of young professionals, but also the organisations for which they work, and their teams providing inspiration and opportunities for growth along their journey. It's open to students, emerging professionals in Australia and NZ, and the winners are recognised with trophies and cash prizes. Besides the prizes themselves, the selected sort of winners will also have an opportunity to present this year's CIBSE seminar series, which will now be fully online. There's a 2020 vision for a 2030 reality. Flights and accommodation are covered, and if the function is currently scheduled for October this year, if that has to be cancelled, obviously due to how the social distancing restrictions develop, we'll make sure to honour this year's finalists at the 2021 function. So please do think about nominating a team member or emerging professional that shows outstanding potential. For those that are here today, you might very well be aware that CIBSE does have a number of different accredited CPD sessions that can be actually arranged outside of sort of the formal CIBSE process. So these are available on the website, and you can reach out to any of these organisations for a CIBSE accredited technology presentation, and CPD certificates for those are available as well. So everyone on today's call will receive a CPD certificate after the conclusion of the session. Final admin slide. ARBS, That's, for those that aren't familiar, it's the Air Conditioning, Refrigeration, Building Services Exhibition. This is one of many large seminars this year that has been rescheduled to 2021, being hosted at the Melbourne Convention and Exhibition Centre. It is metaphorically and literally Australia's biggest HVAC&R trade show. If you want to see a chiller that's larger than a bus, this is where you need to go. It'll showcase hundreds of new products and products and technologies which are set to shape the future, and a focus on emerging trends, technology in the areas of smart IoT solutions, automation, control, refrigerants, energy efficiency, and believe it or not, much more. It runs over 3 days. If you attend, you can connect directly with manufacturers and distributors and see the latest products and applications whilst exploring leading design and innovation in HVAC&R. Keep an eye out for CIBSE. We currently have a stand allocated, but that may very well change. Okay, time for the main event. I'm pleased to introduce Brent Ladbroke from Aquip. Brent has been involved with thermal energy metering and other instrumentation for over 8 years, and in that time has been involved in numerous projects, from selection of meters, selection of metering points, through to installation of meters, and my personal joy, commissioning. Brent is based in Sydney, actually on the northern beaches, so we both dialed in from the beaches, which is usually, you know, jealousy inducing. His role is primarily focused on thermal energy metering. Brent's presentation does run for about an hour. If you do have any questions that come up, please use the Q&A function that you've got through your Zoom app or through your browser. We will keep an eye on what comes through. So as a reminder, there is a Q&A function, which is separate from the chat function. Do submit it through that. We'll keep an eye on it. If we decide it's worth sort of attending to there and then based on the slide, I'll just interrupt and throw to Brent. Otherwise, we'll have a bit more of a formal Q&A session at the end. If you're so inclined, you can ask anonymously. But do note other attendees can see what you're putting up there. So keep it clean, or go on Twitter if you want to sort of say anything else. Without further delay, I'll hand over to Brent. Thanks very much, Brent. And I believe you can take control. Go for it.
Yeah, it's not letting me. I cannot start screen share while the other participant is sharing. Phil, so there we go. Okay. Phil, can you see my screen now?
Not as yet.
Can people see my screen?
Hasn't started sharing it, Brent. Oh.
Now we're good?
Okay. Yep, just throw that up onto full screen. I think we're good. Yep.
Okay. So thanks, Phil. Pleasure to be invited along to present this today. I've had a look in the chat box and the participants, and there's a few names I recognise. So those that I've met before, welcome along. CIBSE asked me to put together a PowerPoint presentation, and this was the first sort of thing that I came up with. And then apparently it was to be on thermal metering, so I thought I'd better write something else about thermal metering. So we wrote this a year or so ago and had it approved by CIBSE a number of times. So we'll get into this. It does take about an hour. So as Phil said, if you've got any questions, just type in the chat box. He'll keep an eye on those and interrupt if he thinks it's necessary. A lot of these things we'll get to as we go through, but a quick overview of who Aquip Systems are, where we fit into the world. We've been around since 1991. We started in Western Australia, now have offices in 4 major cities, so Perth, Brisbane, Sydney and Melbourne. 29 odd years experience in flow metering for liquids and gases, 10 odd years in thermal energy metering. Brent is my name. I've been with Aquip since 2010 and shifted to New South Wales in 2016 at the first weekend of May. So just over 4 years I've been in this great city. What are we going to be going through today? We'll talk about what we're hoping to learn. We'll talk about industry trends. We'll talk about terminology. We'll go through what standards are relevant in Australia and perhaps what aren't. We'll talk about types of meters that are available on the market. We'll talk about considerations for selection. How do we select the right thermal energy meter? Most importantly, there is a test at the end, so you do need to pay attention. I might give you some extra emphasis on things that you need to maybe know for the test as we go along. Okay, so by the end of today's session, we want to be able to understand the fundamentals of thermal metering. We want to be able to have some idea of selecting the best thermal metering option for any given patient. Understand the fundamentals of communication protocols, which is sort of an adjunct to thermal energy metering, but still just as important. There's no real reason in metering if we don't get that information somewhere in a timely and useful manner, and getting that to the right place is important. Understand some basic installation principles, and understand that system accuracy is far more important than any given component accuracy. Okay, these things are probably no great surprise to anyone on this webinar. So what are the trends in the industry? Obviously costs are going up. Who knows what the future will bring on costs, but I'm sure they won't be coming down. Energy costs are often 50% of the energy bill for a building now. LED lighting and various other innovations have reduced the consumption of power on those elements, and it continues to now take a larger percentage of the power bill for buildings, or heating and cooling does. What does that lead to? Increased metering. People want to meter more to know where that power and energy is being used. An example in Sydney recently, Northern Beaches Hospital has 199 thermal energy meters. There's other people who are having larger numbers of that on projects, but certainly there's a lot more meters going in. People are wanting to meter more locations so they can recover cost. It could be an internal type, billing a department or billing a tenant, as in a hospital. It could be a pathology company or an imaging company that has leased part of that hospital, and the hospital wants to get their money back. Ultimately, that cost recovery leads to increased profit for the parent organisation. Some terminology. I'll repeat this slide at the end of the presentation again, so if you sort of don't get all of this straight away, that's okay, we'll go through it again. So sometimes there's some confusion about which is what, but flow rate is our instantaneous amount of flow, whether that be in liquid or in energy. So meters per hour or cubic meters per hour of water going through there. Liters per second is often the units used here in Australia. It could be what is our current kilowatts being used. So it's an instantaneous amount. It's the speedo on our car, whereas the totalizer is, what's the total that's been through for a given period. It's how many kilometres have we got on our odometer, so we can sort of totalize those up. And that's what we typically would bill or allocate at the end of a given period. The velocity is the speed of fluid through the pipe. So typical design speeds for flow would be somewhere about 1.5 to sort of 2 meters per second of flow. Zero cutoff is what the number of, or what the meter will not read below. So for example, if you're a speedo in your car, you have to get up to about a walking pace before it would register anything above zero. Below that number, it just will read zero. So zero cutoff. Turn down ratio is kind of related to that. Turn down ratio is the ratio between the permanent flow rate with a minimum and the minimum guaranteed accuracy. So every flow sensor, every measurement device typically has a maximum or a design flow rate and the minimum guaranteed accuracy. This is to do with velocity of the liquid going through the pipe, and every flow sensor has this ratio. Accuracy is often talked about. Accuracy is really how close to the real number is the reading. You see there with our archery target, accuracy would be we're getting bullseyes every time. If that was spread out, then our repeatability wouldn't be so good. So we're getting a different number every time. But if all of those arrows were grouped together, say, I don't know if you can see my mouse, but over here on the right-hand side would have very good repeatability, but we wouldn't have very good accuracy because we're not hitting the bullseye. We could also have them averaged all over the target, and if the center of that was the bullseye, we'd have fairly good accuracy, but not very good repeatability. So those two terms are often thrown about, and often people are after both, but often they're more interested in repeatability than accuracy. MPE, maximum permissible error. This is a standard or a term out of European standards, so we'll go through as to what makes up those when it comes to thermal energy metering. Okay, so standards. What standards do we have here in Australia? What do we need to worry about? The good and easy answer for that is there are none. So there are no current Australian standards on thermal energy. There's nothing on the drawing board. There's nothing that is likely to happen in the foreseeable future. So we don't need to worry about them. NMI is quite often specified, and I guess if there's engineers here who are making specification of meters, sometimes we see engineers write in the specification that a thermal energy should be NMI approved. Not possible, so please don't write that in your specifications. National Measurements Institute cannot certify anything when there is no Australian standard. So I've had a number of conversations with them, and until there's an Australian standard, which there's nothing on the drawing board, you cannot have NMI approval on a thermal energy meter. Commonly, though, we want to reference something, so commonly European standard EN 1434 is referenced, and I don't think that you could go wrong sort of defaulting back to European standards. They seem to be the leading standard globally. And there's three main classes of standard, or classes of meters under EN 1434, class 1, 2 and 3, given sort of the overall accuracy. So class 2, typically 2%, is really the best commercially available. You can buy a class 3 meter. I don't know of any class 1 meters that are available, but class 2 is sort of the best commercially available meter. So they would be well worth specifying class 2. Some meters will come with calibration certificates. It does not mean that they are approved to EN 1434. It just means they have a calibration certificate. It may not meet what you're after or any specification. Other standards exist. Some of these are specific to various countries. So MID, OIML, OIML, depending on which country you are in Europe as to which metering directive, so MID metering directive, might be specified. Here, of course, we don't have anything, although we will talk about a few things as we go through. Okay, so that's covered standards. So what is a thermal energy meter? Let's get into this. A thermal energy meter consisting of four main components. Must have a flow sensor, temperature sensors, and these temperature sensors, there must be two of them, and they must be paired and matched. Under the standards, that has a calculator, and we have communications to get that number somewhere that's timely and useful, and the right values for whatever purposes we want it for. Please remember, thermal energy meters are not flow meters, but a flow sensor is part of a thermal energy meter. And for terminology, I like to refer to them as flow sensors. I guess in my life, I also sell flow meters where it's purely metering the flow, whereas I refer to the flow sensor when it comes to being part of a thermal energy meter. What types? We can buy these in various configurations. We can buy these as purely heat meters. So this would be if there's a boiler and we're in a cold time of the year. If it's summer, we want to measure maybe cooling. Have a chiller somewhere and a cold water circuit loop somewhere, cooling down where we are. And we can also buy these as combinations. So some people would be familiar with a six-way valve, and then at certain times of the year, you're running heat through the meter, heating water, and it will measure heat. And during warmer times of the year, you would be running chilled water through and measuring the cooling capacity going through that particular meter. Physical sizes are standardized, so it's quite easy. There's some physical dimensions, 3/4 inch thread through to 2-inch thread. And then flanged sizes are available in DN15 to DN250. Over DN50, there's no standard sizes. So these are all straight out of the EN1434 standard. And most manufacturers would have sizes available that would meet those standards. From a cost perspective, though, the threaded brass meters are typically much lower, but the 2-inch meter will not sort of measure its design flow rate is 10 cubic meters per hour, and above that a flanged meter must be used. So if it's a DN100, then realistically you're using a flanged meter or a flanged flow sensor. I've just contradicted myself, haven't I? So a flanged flow sensor. Okay. However, we've spoken about pipe sizes, and flow sensors should be sized to the flow rate and not to the flow or to the pipe size. Although the pipe size should be considered, we really should be sizing these to the flow rate, which is usually available from the chiller manufacturer, sort of the minimum, the maximum, and the permanent flow rate. These should all be considered. We should also consider pressure loss. Thermal energy meters and flow sensors have a very low pressure loss across the meter, but these should be taken into account in the design. And pressure class should be considered. Usually the flanged flow sensors are PN25 and often the threaded ones are PN16, but keep that in mind, specifying what flow sensor or selecting one. And the meter should be, or the flow sensor should be no more than one standard size below the pipe size. So often we see here in Australia that the pipes are perhaps a size above what would be needed for friction and various other design reasons. So often we're able to specify a flow sensor that is maybe one pipe size below what the pipe is in the building, and we'll go into the reasons that we do that on the next slide, or in a couple of slides, but this one leads into it. So we'll see here some typical accuracy curves. So as you see here, essentially as we get to the, and this is a logarithmic, so here's a sort of 0.01, 0.1, 1, and 10. As we get down to the lower flows, our accuracy becomes far greater uncertainty at these lower flow rates. So we don't want to size our flow sensor to be operating down in these areas because we reduce our accuracy. Every component in our thermal energy meter goes to making up our maximum permissible error. And if we look at this equation here, our maximum permissible error under the European standards is the error of the calculator squared plus the error of the temperature probe pair squared plus the error of the flow sensor squared, and there's no reason why that's a large F, that's just a typo. We add those together and we square root that number, and that gives us our maximum permissible error. And the key takeaway from this slide is really that there's no point in having extremely highly accurate flow sensor, but having very inaccurate calculations or very inaccurate temperature probes. I sometimes see people go, well, I'll put in an accurate flow sensor and then I'll write some code in my BMS and I'll calculate this myself. And they're opening themselves up to a huge amount of errors. I've even seen people go and buy an NMI approved water meter and then some temperature probes from somewhere and then write the code themselves and say, well, now my thermal energy meter is NMI approved, and it simply doesn't work that way. So everything adds up equally to our maximum error. Okay. This slide, there's quite a bit of information on it. And I'll bring up the graphic at the bottom so we can sort of understand how these flow sensors are sized. So there's a number of sort of Qs that we have. So Q stands for quantity. QI is the lower limit of the flow rate. QI stands for inferior. QP stands for permanent. And QS stands for superior. And if we look at this graphic here, in this example, it's a DN100 with a QP permanent flow rate of 100 cubic meters per hour. Our QI, so our minimum guaranteed accuracy, is 1 cubic meter per hour, so 1/100th of our QP, and our QS is double what our QP is. So typically we want to operate our sensor in between 1 cubic meter per hour and 200 cubic meters per hour. Under the standards in Europe, not that they apply here, we could operate it over our 200, but we have some maximums. And then this flow sensor won't read any flows over 300 cubic meters per hour. You'll see down here on our left-hand side, there's this small zone here where we will get a reading, but we're getting down to accuracies that are not really desirable between our zero cutoff and our QI. So whenever we're sizing flow sensors, we want to be somewhere in around this range here. Obviously, as we go up here, our pressure loss increases. So yeah, you might just want to pay attention to this slide there might be a question on this at the end of our presentation. You never know. Okay, we have our flow sensor, and the calculator is doing this calculation fairly constantly. So we're measuring the water in volume in cubic meters. So a lot of engineers here will specify flow rates in liters per second. Hydraulics engineers work that way, but the standards are all in cubic meters and cubic meters per hour. So the factor is 3.6. So 1 litre per second would be 3.6 cubic meters per hour, and meters are all sized that way for flow rate. So V is the volume in cubic meters per hour. We want to know the temperature difference, so we have a thermal temperature probe on the one side of the equation and on the other side. So if it's on the outlet of the, on the inlet to the billing area, and then another temperature probe on the outlet from the billing area, we want to measure that temperature difference. So it's chilled water, it's going out at sort of say 6 degrees and coming back at say 12. We want to know both of those values. And then K is the heat coefficient of water, calculated according to the formula in the standards. An example of this, here's a heat meter with the flow sensor located in the return. So it's on the way out of the office area or the hospital ward that you're wanting to measure. It's on the water coming back, so it's a heat meter. So the water is going to be a cooler temperature to what it's going out to the area. In this example, we're supplying water at 70 degrees Celsius. It's coming out of that area at 30 degrees Celsius. And let's say we've got 1 cubic meter of water coming through there. See our formula there. 1 times 70 minus 30, or 40, 1 times 40, and K for water at 30 degrees C, which is where we're measuring, is 1.1561. So we have 46.27 kilowatts of energy. If the flow meter is in the supply, so it's at the 70 degrees point, we have a different K factor. And our kilowatts that we would measure at that point would be slightly different. And this is to do with the heat coefficient of water. So there it's a 45.44, so slightly different, but we're only over 1 cubic meter. So you imagine a QP 150 measuring 150 cubic meters per hour. For many, many years. This adds up to a heck of a lot of potential errors if we don't set up our meter correctly, and we must tell our thermal energy meter where the flow sensor is. It must be specified that it's on the supply or the return side, and then we must make sure that our temperature sensors are on the right side of that equation as well. Some manufacturers will send you a thermal meter and it will tell you that it must be on the return side, and you must install it on that return side. Some manufacturers, some that I know quite well, allow you to install the flow sensor wherever is convenient and then program the calculator as to where you put that flow sensor. So it's far easier to set this up correctly. Most plant rooms that I've been in, it's not always easy to install the flow sensor where it was designed to go for pipe work or various other reasons, and then the mechanical people tend to put it wherever's easier, and they may not put it where it's supposed to be, and then you as the project manager has a bit of a problem. Is what do you do if you can't change it? It can be quite a problem and may not be sort of signed off as being commissioned correctly. Some of the types of flow sensors that we'll come across, there's many types out there. Commonly used types are either mechanical or electronic, and mostly electronic, but we still do see some paddle wheel meters out there in particular. Turbine, seldomly used, but we have a little spinny thing, a little turbine inside a flow chamber. As water comes past, it spins at a speed. There's a magnetic pickup, and every time there'll be a piece of metal on the rotor. Every rotation equals so many litres or whatever the scale and unit is, and we measure it that way. Paddle wheel meters, and maybe this slide doesn't come up so well, but we have a little insertion type probe that there's a paddle wheel on the end of it, and that'll spin. Usually pretty cheap, this type of meter, but very, very susceptible to corrosion, erosion and scaling. I've seen, I know of one site here in Sydney that has told me that they've had to go and collect all their paddle wheels out of their strainer in their circuit because the little rotating shaft on those paddle wheel meters was not made of a rust-free material. So after some time they all rusted and they had to go and collect them all and basically reinstall them. Bits of stuff coming past, no matter how well you flush your system, there's a chance of something getting into your loop, fouling that. They can be installed incorrectly, very susceptible to flow profile anomalies. Paddle wheel meters, if you've got a large pipe, it's just measuring a very, very small percentage of the flow cross-section and could quite easily be out by a decent factor. Or turn-down ratios. So the minimum guaranteed accuracy is relatively high compared to other technologies. And there's no diagnostics. You have no idea whether this is working correctly or not working at all. Just rely on it sort of being as per the data sheet, but I guarantee you it probably isn't reading as per the data sheet. Benefits, typically pretty cheap. They seem easy to install, but could be easily got quite wrong. Electronic, far more flow sensors being used are electronic. Include ultrasonic and electromagnetic or mag flow sensors. Solid state, have no moving parts, so perhaps less subject to corrosion or certainly to fouling and that type of thing. Magnetic flow sensors are always in line. They must be in the flow. They could be insertion or they could be like a flange type fitting. Ultrasonic can be in line or they could be clamped onto the outside of the pipe. How does a mag flow meter work? So we see here it's basically Faraday's principle. We have a magnetic field here in red. We have a volume of water coming through in blue. Faraday's law states that when we do that, we have a voltage that's induced, picked up by these two electrodes here. That voltage is proportional to the velocity and is then transferred or translated into a volume of fluid going past the electromagnetic flow meter. They've been around a long time, and that's basically the principle that they work on. But you have an electric current in the water, so that means that we are still subject to things like corrosion, erosion, scaling, particularly on electrodes. So that's something to watch out for. Installation issues, usually there's a large number of straight pipe diameters required upstream and downstream, although manufacturers are getting better at that and reducing that sort of installation distance. Turn down ratios can be a problem. They're better than mechanical, but typically still a bit of a, not as good as say an inline ultrasonic. Some diagnostics, but not so many. Often used for water metering, often the best inline solution above a DN300 for an HVAC application. Typically low purchase price, typically readily available. Okay, the next slide explains how an ultrasonic flow. So we have no flow, we're simply sending a sound signal through the pipe. When there's no flow, it goes upstream and downstream at the same speed. We introduce some flow, and you'll notice that it goes downstream quicker than it goes upstream. The same as if we swam down a river and then swam up the river, we would go downstream quicker and then we would go upstream if we were swimming at the same velocity and same energy, and we measured precisely the difference in time between two node points. We could translate that into the velocity of the river and the volume using the cross-section of the riverbed. So essentially we're sending a sound signal upstream and downstream, calculating the difference in time. In the top one, it's inline. The bottom one here, we can do that from outside the pipe. So there's no electric current in the pipe, there's no voltage or magnetic fields. It's simply a sound signal. So we're not subject to corrosion, erosion and scaling to nearly the amount that we would be with a magnetic or a mechanical flow meter, flow sensor. But of course there is some very, very minor effect. Applications, inline ultrasonic sensors, available now in sizes up to DN300 and flows up to a QP of 1,000 cubic meters per hour. Typically low purchase price, usually good diagnostics, pretty readily available. There's a number of manufacturers out there, some with more features, advantages and benefits than others. Typically a very good turn down ratio. So this is the number between our sort of design permanent flow rate and our QI, our minimum guaranteed accuracy, typically 100 to 1 or better. And if we took QS to QI, that becomes a much, much larger number. Turn down ratio is 100 to 1 typically, often available up to 250 or even higher as well by special order. Clamp on ultrasonic, as we saw, we can clamp 2 transducers, a minor effective scale builder, typically a higher cost, but the benefit is that it doesn't really change the price on the pipe size, so these could be very, very economic for particularly larger size pipes, but can also be expensive for smaller pipes unless that pipe is already installed and the cost of cutting the pipe and disturbing the flow is a real problem. So large pipes for things like data centers where stopping the flow is really fraught with all sorts of issues and operation problems. These ones are sized purely by the pipe size and not so much by the flow rate. Very wide dynamic range of flow. So this is our turn down ratio. We could go to very, very high speeds. Seldomly would you ever see it, but it's available. The good thing is no shutdown required. So if the pipe is existing and the application is in a hospital or somewhere like that where you do not want interruption to any flows, then nobody inside the hospital would even know that this was happening. You could be in the plant room installing this, no disturbance whatsoever for this type of meter. And excellent diagnostics, probably the best diagnostics are in clamp-on ultrasonics. But they kind of need to be as well to prove that they're working correctly. Other types exist, differential pressure, vortex, seldomly used, but they are out there. Temperature sensors, just as important as the flow sensor, PT 100, 500 and 1000, PT stands for platinum, and the number is the resistance of the probe in ohms at 0 degrees Celsius. So PT 1000 would have 1000 ohms resistance at 0 degrees Celsius and so on. 2 and 4 wire configurations are available. You might want to remember that typically distances of cables more than 10 meters, you would definitely want to go to a 4 wire. Temperature probe, as it's not affected by distance below 10 meters, 2 wire is usually okay, and it's vital to good energy measurement. As said before, I've seen people take an NMI approved flow sensor, buy some temperature probes from the local temperature probe shop. And as an example, no matter how accurate your flow sensor is, if you went down and brought 2 Class B temperature probes from your temperature probe shop and they were unpaired and unmatched, and your delta temperature was 5 degrees, not uncommon in a cooling application, then your potential error from your temperature sensors alone is somewhere in the order of 15 to 16%. So it really at that stage does not matter how accurate you think your flow sensor is or how good you think your calculations are that you maybe wrote using some formulas you found. Your potential error is pretty big, 16%, and no one would ever want to purchase a thermal energy meter with a 16% uncertainty, that's for sure. Temperature probes could be insertion. There's a couple of different ones where you use like a pocket, and then the probe gets poked into that pocket afterwards, or they could be directly inserted via the flow sensor body, via a T-piece and adapter. I prefer the pocket ones because if you, for some reason, need to change the sensor or you want to remove it, then you don't have any water to worry about, whereas if it's directly in the flow, then if you pull this out, you have water, so you have to drain the system maybe, or at least isolate that. This would also mean that the system could be completely tested before the flow calculator and everything was put on. So there's 2 different types on insertion. There's also clamp-on type. These are not allowed under neighbours in Australia, but they are used for clamp-on thermal energy meters. This could be maybe not used for standards, but these typically are approved to standards, but maybe the clamp-on meter is not approved to standards, but the temperature sensors are. My take on it is that you're measuring a delta T, so your accuracy on the absolute number when you're using a clamp-on may not be as good or would not be as good as an insertion type temperature probe, but your delta T would be just as good. So for some applications, these are still very, very acceptable. If you were using a clamp-on ultrasonic thermal energy meter, it still is possible to have an insertion temperature probe if that's what is called for by the client or the specification. Okay, so that's flow sensors, temperature probes, and now onto calculators. The calculator will typically power the flow sensor and the temperature sensors, will record the energy together with other variables, and these are some of the things that they'll record: energy flow, liquid water flow, temperature on both sensors, information about the meter, error codes, was there any faults, diagnostics and historical, oops, I've gone backwards, and historical data. So some of these things were out of the registries. This is actually out of a backnet registry, but you see some of the types of things that would be recorded and available to download. They must be programmed to be on the inlet or the outlet side. So if you're unsure, please look at the meters that are available where this could be specified post-installation, so you don't get into the problem of meters that are purchased and then installed incorrectly and cannot be changed.
Brent, can I just jump in there really quick? There's actually a question relating to this. Seems an opportune time to raise. Yep. That is, just to repeat, how do energy meters deal with variable temperatures? You know, is that K factor set and a fixed value, and why can't calculators effectively deal with variable temperatures?
Oh, they do. So say, for example, and that's a very good question. So say, for example, the flow sensor is on the supply side to the hospital wing, let's say that's what we're metering, then it is constantly looking at the temperature probe, and in the ones that I'm familiar with, that would be T1, temperature probe 1, constantly looking at T1 and looking at that temperature at that flow sensor and constantly updating what is the K factor based on the temperature at that exact time. So if that is a variable temperature, it's looking up to every 2 seconds on a mains powered supply unit. So every 2 seconds as a minimum, it's looking at the temperature, looking at the recorded flow and adjusting that K factor. So if that moves even minutely, it'll use the appropriate K factor at that time.
So despite that, then, just to, I suppose, add to that question, just for my own edification, the K factor doesn't sound like it's solely dependent on the temperature, if you still need to be specific about whether or not it's on the inlet or the outlet side?
So no, the K factor is solely on the temperature, but the K factor really is to be measured at it's based on the temperature at the flow sensor point. So the K factor should be, and it's all programmed into the meter, but it should be using the temperature at the flow sensor point. So if you told the flow calculator, the thermal energy meter, that the flow sensor was put on the return side, and many of them are pre-programmed and cannot be changed from the return side. Let's say, excuse me, it's programmed that way. And then the mechanical people could only put it on the supply side. Then you have the wrong K factor for the volume, or for that temperature, because it's going to think that, let's say it's a cooling application, it's going to say, well, I'm going to have the K factor on the return side because that's where I think the flow sensor is. So the return side is coming back at 12.5 degrees, but reality is it's actually measuring the volume at 6 degrees on the way out. So it'll be using the wrong K factor.
Mm.
Do you follow?
Yeah, I think I'm clear on that now. I'm just trying to think. So it's more around then, if it's purely influenced on temperature, then
yes.
Why is, I'm just trying to think actually now, why is there an impact on location? I suppose it's to the first dot point on this current slide.
Yeah, because the thermal capacity of water varies on temperature. So that K factor affects it's to do with, I believe, the mass of water going past at that point.
Yep.
And that changes at temperature. So it's important that we measure the temperature at the point with the volume. So we apply the right K factor.
Surely that temperature would be almost identical within a short reach of the inlet or the outlet side of the meter.
Oh no, because that could go off and it could, cool, it could be on a whole hospital wing and it might come back, 10 degrees cooler and the K factor would be significantly different. Well, in relative terms.
Sorry, yeah, no, you're right.
So you take a heating application, it could go out at sort of 60 degrees and come back at 30, and as our example before, maybe it comes back at 55, depending on how much heat is taken out of that water. If we use the wrong K factor, we're simply measuring the wrong amount of energy. And that K factor is purely based on temperature.
I'm going to keep it going. If anyone else is struggling with it, I'll come back to it. I'm going to nut it out in between because it feels like then if we've got temperature probes at both points, then the K factor should be the only thing that matters, and it shouldn't matter where, where the flow is being measured.
Yes, I see what you're saying, but it's to do with the volume of water and the amount of energy capacity in that water at that temperature. So we need to know the volume measured and the temperature so we can calculate that exact point. There's quite a bit of technical information. If anyone's interested,
yeah, keep rolling.
For you later. Yeah. So thermal calculators, so all have potential errors, must be set up precisely. Some will store up to 1,400 hours of data, and as you see, 460 days. They all have registries for hourly data, daily, monthly, and yearly. So these could all be downloaded. But of course, if we're using communications, we want to get that data live to our BMS or our EMS or wherever that is. A lot of people will say, I want a pulse output. Not so common now it is in water type meters. A pulse output, people will ask for a pulse meter. There's really no such thing as a pulse meter. There's a pulse output on a meter. Pulse is not recommended. Limited information can be sent. You're only going to send one bit of information, whether that's the kilowatts or the temperature, you've got to decide. And simply one pulse is going to be equal to one bucket of water, whatever you scale it at. The problem is we're limited on how far we can send that signal, and pulses get lost. so they get interfered with by other cables around. They, yeah, if the pulse goes missing, you've got no idea whether it's gone missing or not. So you might send 100 pulses, your BMS or EMS might receive 95. 5 of them have gone forever, and you never catch those up, and you have no idea that they've gone missing. Analog is a current, so scale 4 to 20, everyone's probably heard of that. Again, limited information can be sent. Distance is not so much of an issue. Scaling is an issue though, and of course we can only send one piece of data. We can't send all of the information we'd typically like, and is available on a high-level interface such as BACnet. Modbus is also possible, and meter bus is used widely in Europe, seldomly used here, although it is around. Typical data that you would be able to get from a high-level interface would be all of these listed here, all available as often as you want to go and poll the meter. So it would have an address. You ask your BMS to go and ask a meter number 12, tell me what's in these registries. It's not exactly how they all work, but it's kind of the same. So, you know, how many litres of water or cubic metres, what is the temperature, you know, the inlet side, the outlet side, what is the totalizer value at that time, and that is available to be updated very regularly using an HLI. You can daisy chain, you know, sometimes a couple of 100 metres together, so you're running one cable through your building and able to pick up many metres rather than having to run a separate twisted pair back for every analog or pulse signal that you might have. Okay, installation considerations. For existing sites, I guess lifting considerations for larger meters, or for any site access, lifting considerations, how big is it? How do we get it into location? Do we need a work platform, some kind of force system? For new pipes though, typically inline sensors are used because they're generally cheaper than a clamp-on sensor, but for larger pipes, still worth considering a clamp-on sensor for even new installations. Allow straight lengths free from valves and fittings. So that varies from manufacturer to manufacturer. If you're installing a clamp-on meter, then sometimes manufacturers would say that ideally like 15 straight lengths, 10 upstream from the flow sensor and 5 downstream. Inline ultrasonic sensors, now there's manufacturers who say there's no requirement for straight lengths upstream and downstream. If you are selecting a meter where it says there must be, then please design your plant room with that amount of straight lengths so you can allow the mechanical contractor to install it correctly. Often mag flows will say 5 diameters upstream or whatever. Make sure that you build them a plant room that they can install the meter you've specified in. Okay, for existing pipes, what's the real cost of installation, including loss of flow? Do you know what the flow rate going through the pipe is? How do you size an inline meter? You may have to measure that to know, because the drawings are all obsolete because there's been adjustments to the system since it was installed and commissioned. What are the unknown risks? What happens when you cut the pipe that's 15 years old? Is it going to be able to be flanged, and is it going to pass X-ray tests or whatever tests that you do? Can you tolerate a pressure loss? Is your system designed so that you can install that meter? Is it best on an existing pipe then perhaps to use a clamp-on meter, because you don't have to worry about any of that? But obviously there's cause for both solutions, just depending on all of the ins and outs. Power supply, what power supply is available? Ideally have 10 straight diameters upstream, downstream, not always possible, as we said before. Okay, system accuracy versus component accuracy. For integrated meters, Neighbours is going through some major changes, so we won't specify too much on that at the moment. There's a draft out from Neighbours that I was involved in talking with them about. Previously, they had this sort of 5% accuracy across full sensing range, which is not typically how energy meters work. But they are going through some changes at the moment. There's people assigned to that task. Green Building Council refers to Neighbours. Check what ingress protection you need for your meters. For clamp-on meters, particularly check if your meter that you're about to purchase has a zero calibration. You may find yourself in all sorts of strife and still have to stop the flow to install and commission the meter if your meter is not supplied with a zero calibration procedure or zero calibration having happened to it. Check the maintenance of each meter, check particularly with clamp-on. Some of them need to be reinstalled on an annual basis, and that can be a real problem. Some of them don't. Check which protocols you're after, check which pressure is required, pressure rating. Protocols, bear in mind there's various types of Modbus. There's Modbus RTU, Modbus TCP/IP, there's BACnet, MSTP, BACnet, IP. Make sure that you get the right protocol so that it matches. NABERS, for those who are not aware, National Australian Built Environment Rating System, administered by the New South Wales Office of Environment and Heritage, but I think they might have just had a small change to that recently. So they're based in New South Wales, but typically national. Cost of getting it wrong. Integration difficulties, nothing worse than getting everything right, and then always as, you know, the last 1% of the project takes 10% of the time, making sure that it's going to be read by your BMS. Missing low flows means missing revenue. And remember that selection and installation errors, no matter what the meter or what any sort of sensor, will always subtract from published accuracy. Keep in mind, what are your maintenance costs and recommissioning? What's the cost of getting it wrong? This is
Brent, can I just jump in there again real quick? There was another question just specifically around installation from Alex Troiak. Should new meters be installed with a maintenance bypass?
Typically, that's not done for thermal meters. There's nothing to stop you, but your cost of installation goes up quite a bit. I would see that more in a plant room type situation rather than a sort of a sub-meter out in the field on a level of the building. Typically for thermal meters, that's not done. But you could do that, nothing to stop you, but your mechanical costs are going to go up a lot higher than not doing that. That's my take on it. Mostly where I see thermal meters, there's no bypass at all. If I do see them, they'd be near the chiller in the plant room, so they're fairly large sizes. But that's my take on it. So there's no requirement to, under the standards, to do that, to my knowledge. Continue?
Yeah, sounds good. Alex, okay. If you've got any follow-ups, just ping us again via the Q&A.
Yep. So this is actually on a boiler at a university in Haymarket, and we measured this with a clamp-on ultrasonic just temporarily. It's a DN100, and we measured 855 kilowatt hours in a 10-hour period. And you see there the cycles. So it's quite quite cyclical flow and energy usage, depending on the usage of the building at the time, and how the boiler is being powered as well. So these add up to big amounts of dollars over even a short period of time. Cost of getting it wrong, commissioning. Meters can be validated using a master portable meter. Now, a lot of questions about this, and I know we're getting short on time. I've had engineers say to me that their thermal inline ultrasonic meters or inline mag meters should be validated once they're installed. My take on it is, and I've had engineers tell me that it's written somewhere, and I've said, please provide me the document. And if anyone's got that document, please email it to me, because I've never seen it. You have a meter or a flow sensor that is calibrated, and the volume going through that is traceable back to the 1 kilogram unit in France, albeit now virtual. The temperature probes are paired and matched and calibrated, supplied with a certificate, calibrated to the best of European standards that are readily available. The calculator is calibrated. You install it correctly. If there's no error codes in the meter, I think we're pretty safe in saying that that is working properly. I know I've been to validate existing thermal energy meters it would cost more to validate it because you have to use then a portable clamp-on type meter, clamp that on, and then on the day you go to do it, there's no air conditioning running. So it's reading 0. So the cost of doing this is huge. My take is that if it's a meter that is certified and calibrated and it's installed in accordance with the manufacturer's recommendations and there's no error codes, I don't see a need to do this, and I've never seen any standard or best practice where it says that that should be carried out. Please let me know if you find it. I'd be most interested. But remember, the more diagnostics you have, the more you know about the performance of your meters, and they have error codes you can download. You should validate the data transmission, and neighbours state this, that you should have somebody at your meter display and somebody at your BMS and check that these are reading correctly and that the scale and everything is correct. So that is well worth doing. So you should make sure that what you're reading is the same as what the meter is outputting. That I agree with, that should be carried out during the commissioning. Maintenance, once again, neighbours refer to a 10-year period, but this has nothing to do with the accuracy or the workings of the meter. It's purely to do with, I have 400 buckets on my meter out in the field and I read 400 buckets on my BMS, and that is all that they ask you to test and check. And you should have a plan to do that once every 10 years. And I think you also have to do it within the first 3 years of installation. Just could be corrected on that. That is all neighbours ask. You could install it, leave it there forever as long as you go, yep, it's reading the same on the field as it is on my BMS. That's all they ask. There's no reason or standard to say these should be taken out and tested. Green Building Council refer to neighbours. You could take a portable master meter out there and clamp it on and test it, but once again, can be quite expensive to do. Labour is not cheap, and then you go out there and the meter is not running that day, and you could be there for days and not gather a lot of information because of usage patterns on that day. The bigger the pipe, the bigger the flow, the closer to the chiller you are, perhaps the easier that gets. Under European standards, and this varies from country to country, they'll take out 10% of meters and they'll do that every 6 years. And if a certain amount have drifted by too far, so gone off calibration by too far, you must replace all of the meters in that jurisdiction. So in Europe, there's a very, very strong push to having meters that do not drift. So ultrasonic meters do not drift like a magflow or a mechanical meter. A mechanical meter is going to drift a lot. A magflow, maybe not much, but typically more than an ultrasonic, because all you have in an ultrasonic meter is a sound signal going upstream, downstream. No moving parts, no electrical currents, so far less likely to drift. And remember, if you're a building owner, these meters may be your cash registers. But going back to the 6-year period, I've never seen anything specified in Australia. And people ask me, and I'm going, well, there's no requirement, but you may, somehow want to sort of specify some time period where all meters should be replaced. Usually meters are tested to about 10 years worth of cycles, and bear in mind a heat or a cooling meter is expanding and contracting every heat or cooling cycle. So there is some fatigue on that actual physical flow part in the pipe. So bear that in mind, but there's nothing specified in Australia. Keep it in mind. One day maybe there will be. Terminology, we went through all of this before. If you've got any questions, type your question quickly or send me an email later. Some case studies and we're all but done. This is on a hospital in Perth, major hospital, large pipe, not used for billing, but being used for allocation to departments. Stopping the flow near on impossible, so a clamp-on ultrasonic was used. No standards were required, it's all internal. Can be installed under the insulation, and the insulation mounted back on the pipe quite quickly. Nobody needs to know it was even going on. Paddle wheel meters, this is on a thermal energy plant here in Sydney. It wasn't actually for thermal metering, but it was metering water in a thermal plant. Customer wanted paddle wheel meters. I dislike these things passionately, particularly in this installation, because we have so many bends and getting an accurate reading of the flow profile is near on impossible. So there was quite a bit of work in validating these using a clamp-on meter to set calibration factors of these paddle wheel meters. They used analog signals, so there's no real diagnostics available out of this, and they were working at the time of commissioning accurately. Are they still? We don't know. We don't have any diagnostics whatsoever. I guess we presume they are, but they could be recommissioned. This is in a hotel in Sydney. I don't have any photos of the actual installation, but these are Sydney Hotel where they upgraded their boilers and chillers. And it was a third party that installed the boilers and chillers, and they're selling the chilled and heated water to the hotel and financing it. So they wanted to accurately bill the hotel. How much chilled and heated water are they providing them right now? Maybe not very much, but they wanted something certified to the best sort of standards commercially available. So this is a fully stainless steel flow sensor installed inline, calibrated back to the best standards available for thermal energy metering. Questions? We'll get on to the test first, but if anyone wants, there's my details. Of course, if you don't quite catch those, then just type something in the chat box and we'll get those details to you. Maybe Phil, you write them there anyway.
There are a few questions there, Brent. I think we might touch on. There's a bit of a common theme occurring. So before we send everyone off to do their test and have a little bit of an early mark.
And you can start the test if you like. Either scan that code if you want to get going on the test. Remember, if you do the test, you'll get a certificate from us. If you don't, you won't. Simple.
The link does work, everybody. I've tried that out, so please jump onto that if you're happy to do it. There's a couple of questions here, Brent, just around combined heating and cooling applications. So I suppose one generically is, when might you use this and what are some common mistakes? There was a very specific question around how you might deal with this if you've got a changeover manifold arrangement. See, with heating and cooling having very different flow rates, so you would potentially have an incorrectly sized meter for the different applications.
Yeah, that's possible. And sometimes we see this with very low flow rates as well, where you might have very, very low flows, even on a large pipe, and it's quite difficult to find the right flow sensor. Somebody before asked about bypasses, and I have discussed, I haven't actually done this, and of course it may have been done, where you actually have a valve that will switch. This is not answering this specific question, but there's some buildings with expected high demand during daytime and expected very low demand during evening, but they want to capture it. So the flow sensor required for the high demand is different to the flow sensor required for low demand. So then it would be possible to have some sort of a changeover valve and a bypass to then say, well, with flows of this high, we'll use this flow sensor via the main, and then we'll have a smaller pipe as a bypass, and if flows fall below a certain amount, we'll bypass the flow into that flow sensor. That is possible to do. But I guess if it's going to be measured on the same pipe and you don't have a bypass, then yeah, really it's a case of looking at what is the best selection. So we talked before about dynamic range. So it's really looking at, well, what are the expected flows? What is the expected high flows? What is the expected low flows? And then just sizing that meter the best possible way. So we also spoke before about dynamic ranges. Typically, by default, these are 100 to 1. And in instances like this might be an example where you have a dynamic range or a turn down ratio of 250 to 1. So you can capture much lower flows. So they're a little bit more expensive because there's more calibration that goes into them. But where you have high ranges and you want to capture them at both of those accurately, then this wider turn down ratio might be well worth investing the money in. And until I saw the exact flow rates, it's hard to comment further.
Yeah. Look, that sounds like it could be a specific question. So that one's from Matthew. If you do have a specific, I think, application there, I'd suggest just contacting Brent separately. I'm sure he'll be happy to answer.
Sure.
Another one that's just come through, I'm just racking my brain as to the application in building services, but what about fluids other than water, for example, refrigerants or chemicals?
So yes, they're quite possible. So certainly with a clamp-on meter, that is quite possible to do. You just program the meter to what it is. It might be a glycol mixture. We don't typically see that in Australia, but there would be parts of the world where that is used. And you can program that. I believe it's also possible with an inline ultrasonic meter, although I've never actually had to do it here in Australia because I've never seen glycol being used. Maybe it is somewhere. And I'm not sure about mag flows, but it is important because that energy or the K factor would vary from fluid to fluid. So just make sure that if you're purchasing or specifying, you make some inquiries with myself or with your local, whoever it might be, to make sure that that is possible with whatever you're specifying. It certainly is with clamp-on, certainly is with inline ultrasonics. From my readings, but I've never actually done it, and I'm not sure about mag flows. But it is important.
No problems. And there was one further question just on K factor, so that's obviously got everyone thinking.
Yep.
Can you average the flow and return to come up with a K factor? My gut feel is, I suppose how much of an error might that introduce? Is there a significant difference in K factors?
Well, I don't know if I understand the question. So average the flow and return temperatures or average the flow and return volume? I'm not sure what they...
I think we're talking about a location independent K factor based on the average flow and return temperatures. That's how I've interpreted it. Alex, sorry, that came from you. If we've understood that differently, let us know. So I suppose what impact might that have to try and make it an idiot-proof installation?
Yeah, that's something maybe with some drawings I could draw that out a little bit better. So if anyone does have specific questions on that, let me send either yourself an email or I guess, did you type my email in the chat box? Maybe I can. But brent.ladbrook@aquip.com.au.
And the session will be available as well for everybody. We've just got your details on this, so that's fine.
So we'll go through those. We'll go through these answers, or were there more questions, Phil?
Nothing else has come through, Brent, so happy for you to spend a bit of time with the class and so wrap up.
Well, yeah, thanks Phil, thanks very much. We'll go through these quickly so those that have finished and done with us can sort of get on their way. So name 2 physical types of flow sensors used in thermal energy meters. So this would be magnetic clamp-on ultrasonic, inline ultrasonic, paddle wheel, any 2 that you choose. Question 2, is pulse output usually the best option for communication? Clearly the answer would be no for lots of reasons. This next one is a mathematical one, and as I reach my calculator, how much energy would be unaccounted for and until using 5,000 kilowatt hours per week with a 4% meter error? So it's simply 5,000 times 4% times 5,000 times 4%. Is 200 times 52 weeks, 10,400 kilowatt hours could be unaccounted for on that error. How much would that equate to? So the answer for number 3, 10,400. Number 4, how much would this equate to if energy prices were 31 cents per kilowatt hour? 10,400 times 0.31, $3,224. Question 5, what flow sensor type would be a good consideration on a DN500 existing pipe in a large data center for chiller balancing? Large pipe, it's already there, data center, we're balancing, we're not billing, so a clamp-on one would be an ideal consideration for this. Okay, question 6, considering a meter for a DN50 pipe, typically low flows, how would you select the right inline sensor? And I think this is a multi-choice question and it's using all the minimum, maximum flows. So I think it's pretty obvious what the answer is. If an inline sensor has a permanent flow rate of 50 cubic meters per hour, what is the typical maximum allowable quantity superior? If you remember from our chart before, it's typically double. So the answer would be 100 cubic meters per hour. And question 8, what is the minimum the same meter would read, assuming a turn down ratio of 100 to 1? So the QI for that would be 1/100th of 50 cubic meters, so 50,000 litres. 1% of that is 500 litres per hour. Are there NMI standards on thermal energy metering in Australia? If anyone answers yes, my mission has been unsuccessful, so it's not possible. And the last question, you are running temperature cables 25 metres. Are you best to use 2 or 4 wire sensors? You may recall before, anything over 10 metres, definitely go for a 4 wire sensor. So if you have any questions, hang around. We could even turn microphones on if anyone wanted to hang around, or email me, or do whichever you like. Thank you.
Thanks very much, Brent. I haven't seen any other Q&As come through, so it might turn into a bit of a riot if we unlock everyone's microphones. It's probably just most appropriate. They send you an email or give you a call afterwards, Brent. I wasn't sure if you wanted to just throw back to the previous slide there, Brent, while I do a quick wrap up, just so anyone can access that quiz if they want.
Yep. So put the camera at the QR code or type in that Google address. Sorry, we couldn't make it clickable for this.
No problems. We've already had a bit of attrition as we've sort of gone through the questions. So look, I'm just going to do a very quick wrap up. First of all, thank you again, Brent, for taking the time. And for everybody that's still here, thank you for dialing in. We appreciate it. Reminder, a copy of the session will be made available as a recording on the CIBSE website quite soon, and the presentation itself as well, just if you want to go through that in your own time rather than listening to Brent babble on. That's there for you. As a reminder, all ANZ sessions currently will be made available to everybody to attend. The next New South Wales session is looking at education as an asset class on Tuesday, June the 2nd. I'm based in Sydney, so when I think of some of the more recent uni campuses that have gone up, UTS, University of Western Sydney, most of those much more closely resemble a commercial building than anything I studied at 10 years ago. So, with that, I will wrap up. Thanks once more to Brent for his time, and we look forward to seeing you at the next session. Have a great day, everybody.
Thanks very much, everybody. Thank you.